All right, welcome back to COG 376. Today we're going to continue on in our exploration of the different ways we can model language and talk about how we can capture semantics or meaning of language in a computer model using vectors. So, first, big question is, what do words mean? This is a broad, kind of a tricky question in certain ways. For example, you see this symbol, you know what it is. It's three letters, C, A, and T, but you know what it means, right? Cat. You know that it means the fuzzy animal that likes to knock things off of shelves, right? You have an understanding of the meaning of the label, the symbol cat, and the symbol being the spoken word, but also the transcribed physical, visual version of the word, the word, the letters, right? And that's the idea of semantics. Words are these symbols that are going to signify something else, right? They're a reference to something that is more complex. And they can be tied to real-world experiences, like cat. You know, we've pretty much all of us have seen a cat in person, but also car crash, for example. That summons up a pretty complex and vivid image of various objects and events all at once. You may have been in a car crash, you may have seen one before, but man, those two words, those 8 letters and a space, really ties to a lot of meaning. You can there's all these moving parts that you can internalize or you can remember directly, and that is a form of semantics, the experiential component, the simulated component of it. But in a different way, you can also tie semantics to other words. You know, you don't always have to have a physical, visceral experience to understand the meaning of a word. You can actually just hijack other words and let them help you understand what a word means. And that's how definitions work, right? So definitions allow us to use the semantics of several other words to build up the meaning of a particular word, right? So you don't have to directly experience it, but you can construct indirectly from other words some kind of meaning. For example, you see these kinds of entries in dictionaries all the time. Cat, noun. Well, not these are my own, right? But if you had never seen a cat before, a furry animal that likes to knock things off tables, like I said before. Capybara, maybe you haven't seen one before, right? Noun, the world's biggest, chillest rodent. I can show you one. Now you have a bit more of a visceral experience of seeing a capybara sitting under a hot spring tube, whatever we call this, fountain, having a bath, right? It's a chill rodent. But before you see this image, you still would have had some idea. You know, the words big would mean it's a little bit bigger than other rodents. Chill means you kind of have an understanding of its temperament. Rodent means you kind of know what kind of animal this is. And you know that it is an animal, right? So, that's the idea of you can bundle up new meaning for a word into from other words. So that brings us around to the ideas of words, lemmas, senses, and definitions, right? So you can get a little more complex than just one straight up definition. Words can be used in multiple ways. So the lemma is the dictionary entry, right? The part, including the part of speech like noun or adjective, right? It clearly there can be different lemmas for one word, right? You can use the word tap could be a noun, so that would be the object that emits water, or it could be the verb to strike something lightly, right? So lemmas give sort of the broadest categorical changes, right? But even within a lemma, there's different different ways to use the word, different senses. So, for example, the verb run might mean human jogging, it might mean machinery moving, or it might mean somebody organizing an event, right? all different ways to bundle up meaning into the same single, symbol of the word. So you might see dictionary definitions like pepper in. So it's got all these different. So that's the lemma, right? This is the noun version of this word, and it's got all these different senses, right? The spice, the plant, all these different kinds of things. The way you might refer to the food item like peppers, like a pepper tree, right? And for each sense that there might be is going to be some kind of definition, right? So that's the way. This is like sort of the most long and short, I guess, is the way to put this, of how we can bundle up meaning using other words that are perhaps more basic or related to other things into a single new word. So that's the idea of relating words broadly. But one interesting thing is sometimes we're concerned with how close in meaning two words might be. So we can relate one sense of meaning for one word with a sense of meaning for another word. The senses, the definitions of different words can be connected in some way. So here's, for example, one kind of relation. Synonyms, right? Words that have the same meaning in some or all contexts, right? So couch and sofa, those are pretty much the same. Big and large, auto and car, maybe not always. Auto has other meanings, right? But in certain capacities, you've seen the word auto and you kind of know, oh, that means, this is a car shop, right? Vomit and throw up, that's a pair of words, but still they sort of go together, right? Water and H2O, H2O is a more scientific notation for the same material, but they are fundamentally the same. You could exchange them in common usage and people would sort of get it. And essentially, there's no real examples of perfect synonymy, right? Even if a lot of aspects of the meaning are the same, there might be a little bit different things like whether or not you're using slang, what genre of writing that you're in, that kind of stuff. So regardless of couch versus sofa being almost identical, there's subtle differences, right? Otherwise we probably wouldn't have two words for it. So that's on one end of relations, right? Things that are very almost the same meaning but two different words. On the other end, but also a little bit contentiously, is antonyms, words that mean the opposite of each other on one particular feature or sense. So, for example, dark and light, right? These are opposite meanings. You would never mistake, oh, I walked into a dark room versus I walked into a light room as meaning this exact same thing, right? They mean almost completely opposite. Fast and slow, hot and cold, in and out, short versus long, rise and fall, up, down, tie, untie. And so these are all different ways you can represent sort of opposition, right? Binary opposition, so like things are either inside or outside, things are either dark or they're light, or maybe at the opposite ends of a spectrum, like short and long, fast and slow. They can also be reversives, which is just a quick way of saying like they can be a verb that will undo each other, right? So if you rise and then fall, you've done the same thing, or an adjective that will describe I'm up or down. But here's the tricky thing about this. Even though these things are in direct opposition in terms of their meaning on the one feature, right? How bright is the thing? They're otherwise actually extremely similar in other ways. They often describe the same feature. They're used in the same way. They are actually very much related, even though they mean opposite things. You wouldn't say, for example, light and bright. Do those mean the same thing? Sure, yeah. Are those relevant? Are they related? Okay, how about light and dark? Those don't mean the same thing. Those are opposites. Ah, how silly. What a strange thing to suggest. But then you have something like light and saxophone, which have just almost absolutely nothing to do with each other. So even though antonyms seem to have this powerful difference from the two meanings of two words, they actually still are quite aligned in terms of all the other sort of subtle ways that words can be related and connected to each other. So those are two examples. You also have a softer example. So another relation is just sort of a general sense of similarity, right? So some relations don't have to be as extreme as syn/antonyms, right? Synonyms, antonyms, but they can share some element of meaning, even though they don't mean the same thing, right? Car and bicycle. We know they are both things that can be ridden or that can help you locomote. Cow and horse. They're both ungulates with certain things in common, right? Actually, they may not be ungulates both. Doesn't matter. Table and chair, for example, they are two things that they share something. They're both used in the same way. Fur and feathers, both kind of coatings that you can have on a body. So they're not synonyms, certainly not by a long shot. And they're not antonyms. They don't mean the opposite of each other. We just have this general sense that they are somehow related. They are in some way similar. There are other relations that we won't dive into deeply. Things that are connected but not necessarily similar. So that can just be generally relatedness, right? A car and gasoline, right? They actually don't do both of the same things at all, right? It's not like horse and cow or car and bicycle. Car is a very different object than gasoline, but we know they are connected. They're part of a broader system. They're part of a similar action. We know that one depends on the other, at least for now. We'll see where tech goes in the next decade. But yeah, car and gasoline are words that are related, but not necessarily similar, right? Another one is the semantic field. So there are words that might cover a broad domain. So for example, hospital is related to all kinds of elements that are within the same domain, right? Surgeon, scalpel, nurse, anesthetic. These are all things you would find in a hospital. They're all connected by way of the environment in which they typically exist, or some kind of category in which they exist. Speaking of categories, so super and subordinate. So there can be more and less specific terms. For example, vehicle is the broader version of car, right? Because there are other kinds of vehicles. But you do know what a vehicle more or less contains. You can have cars in it. Fruit is the broader form of mango. Furniture is the broader form of chair. Now, there's an interesting thing here. Some of these are more privileged than others in the sense of some of them have direct meaning and some of them don't. If you were trying to imagine a furniture, that wouldn't quite work for you, would it? But point being that there's lots of ways to relate, right? There's lots of ways that meaning can overlap between two words, and that we can sort of have a sense of how those words are related, or at least how much they're related, right? So there's lots of varieties, right? We see lots of ways to characterize how related two words' meanings are. Synonyms, antonyms, similarity, fields, relatedness, all this stuff. But how do we measure relatedness? Like I said before, one benefit of our being humans is we can just do it to some degree, right? Humans have some innate sense of how related any two words are. So to start, we might just ask humans to rate similarity of various words. And in fact, these kinds of studies have been done all the time. There's a pretty large data set here, the Simlex 999 data set, where humans were polled to rate the similarity of certain words. For example, how similar is the word vanish to the word disappear? On a scale of 1 to 10, 9.8 is the average on that one. How about behave and obey? Related, although behave certainly has a different whole category of things when you're talking about science, whereas obey is a little bit more authoritarian. Um, Belief versus impression. Now again, we're drifting, right? Beliefs are more abstract. Impressions are more. You can actually have art that is impressionistic. You don't have really art that is beliefistic, but they still have an overlap, right? They are not unrelated. They are connected in some way, and people, given the chance to rate these kinds of connections, they rank them lower than vanish and disappear. Muscle and bone. They're very different, but they're still connected, right? We know they have things to do with each other, even though they are fully, distinct entities. Modest versus flexible. You might initially think, oh, I can sort of see the connection there, but it's not really. It's kind of tenuous, right? The average ends up being less than 1. Whole and agreement. That's almost nothing. Right? Those are one is an abstract concept, social construct, and one is a lack of floor material. They are almost nothing to do with each other. So that's a way that you can access similarity by way of empirical study, right? But we're not here to talk about how to run human empirical models of language. We're here to talk about computer models. So it's tricky, right? It would be tricky to have humans in the loop at every step when you're trying to compute relatedness, right? First of all, it's expensive and slow. You're not going to run a new study every time we want to know the relatedness between a pair of words, right? There's millions of words in the dictionary, and that means there's millions times millions of connections between words in dictionaries, right? So we're not going to get all of this data all the time, and also it could probably shift over time. But on the other side of things, it's not necessarily objective, right? Not that any sort of thing based on human data can be objective, but humans have varying opinions on these things. We're going to revisit this later. It's important to keep in mind, actually. But it's also, it's a more difficult thing. It's a little more slippery. You ask any one given person, they might have a different opinion about the relatedness of two words. So for our purposes, we could do with something a little more automatic and mathematical. Welcome to Vector Semantics. So, our goal in the computer model language world is to, in this particular instance, model meaning, right? Say we want to design a language model that's aware of these sentences. I have to feed the cat. I have to feed the dog. I like to pet my dog. Those first two give us some understanding that the words cat and dog, they got to be similar, right? They are both used in the exact same way in that sentence. And on top of that, we have additional layer of meaning as humans. We understand they both need to be fed by a human, right? We can see that they are used identically in that sense. What we'd like to do, though, is have a system that could be capable of realizing that, in all likelihood, this sentence also follows, I like to pet my cat, even though maybe it hasn't seen that before. Because I like to pet my dog, if cat can be substituted for dog, then perhaps this is a valid usage of this word as well. So to do this, we need some way for the system to evaluate relatedness of various words in context. And again, we can't just rely on humans to spit that out for us all the time, right? So if we want to represent how related things are, we can use a nice metaphor of distance. So if we want to represent the distance between two words conceptually, it's natural to kind of frame that question in terms of math, right? Distance makes sense numerically. You can see here a sort of a clustering, a broad clustering of words, right? Very good, amazing, terrific, incredibly good, fantastic. Those are all connected to each other. Whereas dislike, incredibly bad, bad, worse, worse, they're going to be further away, right? They're not going to be connected to all those other words down there in the same way, at least. It's very broad. It's very, when I say broad, I mean like it is very abstract in a lot of senses here, but because there's no literal actual physical space where these words live in some coherent connection, right? But what we're trying to do is build such a space that is actually meaningful and can capture certain relationships and such. So, first, let's just talk about how are numbers related, right? We've talked about how words can be related. Let's talk about how numbers can be related. So, simplest version of relation of numbers is you can just do subtraction to show how close two values are. On this number line, 75 exists, 50 exists, and 40 exists. The distance between 40 and 50 is only 10, whereas the difference between 50 and 75, rather, is 25, right? 40 and 50 are more similar, are closer together than 50 and 75. I didn't have to tell you that, but I think it helps to show how dimensions will scale up. So we can also do this with more than a single value. A single value isn't going to buy us much. You know, a single word, there's no chance it's going to meaningfully relate to a single numerical value. But what about a couple of numerical values? Well, with two values, this is a vector now, a point in space, right? You could do something like calculate the distance using our old friend, the Pythagorean theorem. More, we will actually end up doing angle between them, but just to get the point down of distances between. So here's one point, one vector, the vector 1, 4. So it's over, its x value is 1, its y value is 4. So it's over a little, up a lot. 4, 1, on the other hand, is over a lot, up a little. And then 3, 2 is somewhere in there. You do the math out, you get the distance of 1 between that middle vector and the bottom right one, and a distance of 2.82 between that middle vector and the upper left one. That middle vector is more similar, closer to the rightmost vector than it is the top one. And so on up the chain. Two values is not going to be that much information, so we couldn't expect, just like with one value, you're not going to capture the semantics of language with just two numbers, right? But similar mathematics can apply as we increase the number of dimensions. You can always compute the angle between any two vectors, even if you have 3, 100, or 10,000 values in those vectors. Hyperdimensional vectors, right? You can have as many numbers together as you want. You can always still compute cosine similarity. That is the angle between the two. So we can always find a way to find angles between these multidimensional vectors. So, okay, so now we've got ways of comparing big, hairy blobs of numbers. What does that have to do with words? Word embeddings are the ways that we get words converted into mathematical vectors. How do we embed them, a single word, in some kind of mathematical space? If you think back to definitions, words are often most related when their senses can be used in the same contexts, right? So one route is to try to capture, hey, what words occur nearby this word under most circumstances? To start, we can go with this bag of words model. This is the idea that you can represent a word's context without paying any real attention to their order or structure. You just take, hey, a word occurred in this window, say a page, a paragraph, a book, a sentence, whatever. It occurred together with all the other words in that situation. So from there, you start counting. How often does this word co-occur with the other words within that window? So the idea is that we can build a vector by counting the number of occurrences of different words together. Let's keep walking into that. How might this look? So to do this, you can build what's called a term context matrix. You can construct a context vector for each word in the language that we're modeling. So let's look at some language, right? We have sugar. Sorry, let me compose these. So we have, these are the primary words of interest, right? In the middle here we have apricot, pineapple, and computer. The context of those words are the other words that appear nearby. You could limit it to some certain range. You could limit it to if they occur on the same page, same paragraph, like I said before. But The idea here is that these are words embedded in their context. How do we convert this to something numerical? Well, you can build a numerical vector. The way you would build such a vector would be to have one value for a given word that you're interested in creating a context vector for. You would have one value in that vector for each word in your vocabulary. That's a lot. So say from aardvark, we're going to skip a whole lot here, but digital, data, pinch, result, sugar, and so on. The vector length is always going to be the number of words in your vocabulary. That's a lot. That can be quite a lot. And so, it's not necessarily the most efficient format. But the idea is also we can still do some powerful math and vector-based math and linear algebra. Computers can do that pretty well these days. Distributed computing. Or perhaps not distributed. More like graphics processors, right? Parallel computing. So, point being that for a given word, you can construct a vector of the occurrences of other words that represent its context. So apricot, it doesn't see aardvark at all in its context. Doesn't see the word digital. Doesn't see the word data. It does see the word pinch. All right, cool. Doesn't see the word result. Does see the word sugar. Okay. And so on for all the words possible. Again, there's going to be a lot. We're just looking at a little tiny slice of them. Pineapple. Well, how is pineapple used? Aardvark, no. Digital, no. Data, no. Pinch, sure. Right? Result, no. Sugar, yeah. Now, this is not fully representative of what's visible right here. Just think about it in the context of they're both in recipes, right? So apricot and pineapple, they are both used in the same kinds of recipes. We know, the humans, we understand, those are both fruits. They're both sweet. We would understand that. But the computer is trying to infer that connection by logging these kinds of, these context vectors. Now, to contrast, the word like computer, it's going to not have aardvark. It is going to be co-occurring with digital and data, but not so much pinch, result, and sugar, right? These are three different vectors, very small. They're limited in their scope here. But we can see how two of these vectors are just completely overlapping, and while the other vector is just completely different, off in its own world, orthogonal. It is not, the computer is not at all related to apricot or pineapple based on these data that it had, the language that it has observed. So, this must still feel a bit abstract, right? We're talking about some numbers are lit up in one example and some aren't in the other example. So what often helps is to reduce these to sort of meaningful vectors in a visual space, because remember, we're working with hyperdimensional space. We can also work with a more straightforward space. Let me show you what I mean and hope the illustration will clear anything up that's not coming together for you yet. So, to visualize cosine similarity, it helps to just reduce it to maybe 2 or 3 specific dimensions that make sense rather than focusing on this huge, gigantic vector. So, for example, let's look at the vector for these 3 different context words, large, data, and computer, and the word apricot. Sure, you can have large with apricot. That makes sense. Digital size isn't really, you don't really think about that. Maybe big sometimes, but large is more about physicality, right? So not much in that world. But data and computer, heck yeah. And we see multiple occurrences. We'll talk about that in a minute. And then information, there's a large amount of information, sure. Information and data occur a lot together, and computer is certainly going to be occurring with information. We can represent these 3 on dimensions like, we can contrast the dimension for data and the dimension for large, right? So apricot lives over there on the left It only has large. It doesn't have anything about data or computer in its context vector. Whereas dimension 2, data, we see digital is on that axis, but then information has a bit of both, right? Information has a lot of data, so it's very far to the right there, but it has a little bit of large, right? So in this case, we see that information is a whole lot closer and more similar to the word digital than it is to the word apricot, though it does have a little bit in common with apricot. They both have a quantity, a size element to them. So this is the picture of how, it's a pretty good one to fix in your mind of how relatedness can come from these mathematical representations, right? Digital and apricot have nothing in common, whereas information has a little overlap with each, but much more with digital. This is just a way to visualize. Remember, in reality, we're in the hyperdimensional space. So, one thing to note here is that in this case, we've actually taken into account the number of occurrences, right? So information is this huge vector. What does that mean? Well, let's talk about that. You can count multiple occurrences of words in context and include them in the vector, right? Occurring more often would make the points become more distant, right? So the end points are more distant, but really it's only shifting the angle of the vector slightly. So for example, again, our friends aardvark. So digital, the word digital, is going to overlap with computer a couple of times, data only once, result only once. Okay. Information though is getting computer, lots of data, little bit of result, no sugar, no pinch, no aardvark. They both have the same representation, but again, they're going to be in a different space. They're going to be a little bit stretched out from one another. So if we look at that, we see digital this is the data and result panel. Digital lives at 1,1, whereas information lives way over at 6,4. It's okay for that to sort of change. Think of it as averaging. You know, every time you see the word data and not the word result in one of the contexts for the word information, it knocks it over a little bit more towards data. It's not about the distance between the endpoints of these two. It's about how often they're used. So it's kind of a normalizing process. So the whole idea is that we try to capture this by way of measuring the cosine similarity, the angle between the two vectors. So frequency matters. It gives us a sense of, you know, maybe a word is more related to one of its constituent context values than it is to a different one, right? Information is a little more related to data than it is to result, right? But there are some issues here. So frequency clearly helps us build up this meaning. You know, if sugar appears near apricot a lot, that's useful, right? We need to know that. But not every word is as useful as every other word in terms of defining the context. Super frequent words like the, it, a, at, right? They don't help very much. Because remember, the observer here is fairly naive. It doesn't have access to the actual underlying deep meaning structures here. It only really has access to the surface level, like, okay, here's the words that occur together. And the idea is that you want to be able to differentiate one word's context from another, right? So including the words the, it, and a, and at, they're so common that it actually just kind of blurs the edges between the more interesting and more meaningful words, right? Sugar and apricot they're not super uncommon words, but I mean, I guess in a sense they're actually quite uncommon because they are rarely used in, say, a math textbook, right? Whereas the words the, it, a, and at are going to be in there as often as anywhere else. So the point is, if I'm taking a snapshot of what's happening around a word to get its context, then these words aren't really helping. They're just kind of noise. So what we can do is translate this to a different form called TF-IDF instead of just raw frequency. Let's talk TF-IDF. You won't have to compute this. There's a better, you can look this up more rigorously elsewhere. But the idea is so that you understand it, TF is term frequency, the number of occurrences of the word in the document. Document here means the context, right? How often does that word appear in the context? This is the same as what we were just doing, right? We see a word in a context, we add it to the vector value for that word. IDF is inverse document frequency. Okay, what is that getting at? So this is mathematically the number of total documents that contain that exist, right, that we are observing, divided by the number of documents that contain that particular word. So across all contexts, how common is this word, right? And what you do then is you multiply TF by IDF. What it boils down to, this is the key thing for you to understand, the frequency of the word as it occurs in context with the word of interest, but with a penalty applied based on how common that word is. So, okay, we're getting at here, why bother with this? It's a nice, clean mathematical way to sharpen our math, right? We're trying to calculate meaning from math, and it's as a way to sort of zoom in to the proper parts, the parts that have more meaning, right? So infrequent words are going to be the most indicative of some kind of unique meaning, right? At least, how they occur with a word. So, for example, the word hypertext is incredibly specific to certain types of computing. So if another word co-occurs, it's a good indicator of where that word sits in meaning space. Hypertext should be very valuable to understanding the context of another word, right? Documents, HTML, website, all those things, the fact that they occur with hypertext should be super meaningful. Whereas very frequent words, they don't do much work to signify how another word is being used. The word go, for example, you can use that anywhere, and it's not really helping us to understand a word that it co-occurs with. We're not really building up a good, meaningful context for a given word when we include the word go and we weight it the same as something like hypertext. So altogether, what this does is help us focus our vector's mathematical representation on things that are more meaningful and ignore the things that are less so. Maybe not ignore, but at least downplay them, right? So, altogether, that's the idea of context-based embeddings. I hope we're seeing now that you can include the frequency of nearby words can help us build up a mathematical representation of a word's meaning, right? The form of that math is great because we can convert everything to numbers, a vector of numbers, that lends itself super well to the idea of distance in terms of the angle between the vectors. And we also see a way to focus that math onto the more relevant parts of language using TF-IDF. There's lots of other tools, lots of other ways to tackle this, but this gives a pretty complete rundown of how to represent certain amounts of meaning in a mathematical sense for a computer to use. Yes? So let's talk about that. How do we use word embeddings? Not just for our computers, but also just like what can we get out of these? So we've come up with this way to convert words into vectors and approximate their meaning mathematically. So once a set of context vectors is created for the words in the language, you can apply a lot of different concepts to this. So for example, you could use these context vectors to help with replacement. Say you want a system that can suggest alternative words, right? Straightforward enough to just run a quick search for terms that are closest to a word to be replaced, right? We want to replace one word like dog with a word like, say, cat, right? That sounds super boring, but remember, this is the toy example to keep fixed in your mind. It can spread out from there. So measuring the cosine similarity between dog, the word's context vector, and the vectors of a bunch of other words in the language. So cat, chair, banana, And chair and banana are going to be far, far away. You're not going to get a strong connection between those words. But things like cat will end up quite close. They would be a tolerable replacement, right? Now, this would be super on the expensive side to brute force this, but there's other ways around that. That's not the focus of this discussion, right? But there's an extra power here because we've converted everything into a mathematical space. We can do cool things like specify tolerance values for replacing the word. A tighter tolerance value might say, hey, the replacement word needs to be very close to this word. We need things that are just complete synonyms. But you could crank up that tolerance value into something a little looser, would allow for a broader array of similar and not exact options, right? You introduce this mathematical way to represent, hey, how close in meaning must this replacement be? Another cool way to consider how to use these types of algorithms is disambiguation. Consider the phrase, I've got to go work at the plant today. That can mean a couple of things, right? One is much more likely. You already know that. The word plant can mean various things. It has different senses available. The way you can extract this mathematically from our models is you take the context vector of the word plant, and from this, in this single utterance, to see which words come closest. Words that we know to be related to the word plant, say like tree and fruit, are actually going to be a lot further away from this very specific context vector than words like context vectors for things like factory and workplace. This specific context, you can generate a vector that you can then compare against the set of vectors that you have available. You can disambiguate. Which sense was most likely meant? The one about work and factories and electricity and all that crap, right? As opposed to, I'm not going to go work at the Apple today. That just doesn't make sense. So that's a form of using these kinds of semantic meaning tools. Another very interesting one is analogy. So a very cool feature of these semantic vectors in this huge hyperdimensional space, right, is that these mathematical relationships also serve as stand-ins for semantic relationships. So think of it like this. Word vectors all originate from the origin, right? They're all kind of coming from 0, 0 up to the point that they're at. You can also compute the difference vector between two words, right? So Paris and France are going to have similar difference vectors as Rome and Italy, right? Meaning that we're capturing the relationship capital of, right? City in, right? So from France in this hyperdimensional space, the trajectory, the relationship vector between France and Paris means that you could then apply if you apply that same transformation vector to Italy, you're going to wind up at Rome in the semantic space. For example, the translation between man and woman in the semantic space maps to the same differences between things like uncle and aunt, king and queen, because all of the subtle ways that language is used nearby these words is going to put them very close together, or not close together, but they will be different in the same ways as one another. Yeah? That track? So for example, king, the plural form of king, kings, that pluralization vector is the red one here. So from king to queen, we've got the same thing as from man to woman, right? But the difference between kings and queens is also consistent. We're seeing that there are two different sort of relational vectors here that allow us to transform one word into a different form. Now, these are just notional. Let's look at some that were generated from actual data. I don't know the actual what like features that the x-axis and y-axis are touching on here, but you can see that these are all sort of gendered terms, right? Man and woman. The transformation between each of them is very, very, very similar, right? The usage of each word in its context, as detected by this vectorization method, is capturing a mathematical relationship that sticks around, right? Sir to madam. It's a little different because the ways that those words are used are different than the way that man and woman are used. In fact, that's why they live in different points on this space, right? But the idea is that the vectors between all of these, they look quite alike, right? Emperor and empress, duke and duchess, earl and countess, king and queen, uncle and aunt. They all have this difference between the pairs. They have it in common. It goes beyond just, gendered binaries, of course. You can get into degrees, right? So the difference between slow and slower is consistent to most differences between something and the version of it, the relative stronger version. But then est is even further. Again, same trajectory. Slow to slower to slowest has a similar shape from dark to darker to darkest. A little different here on like clear and clearer and clearest, but again, this general shape, this general mathematical differential shape is consistent. I just find that fascinating on its own, but it kind of hangs together, right? We have done the due diligence to convert these words into mathematical representations that are consistent, and they're based entirely on context. So that's the idea of analogy vectors. We're not always going to know why a given relational vector has a particular shape. Why is slow to slower kind of angled one way and slower to slowest angled a different way. But you can always discern that shape when we're in this hyperdimensional space. Remember that there's thousands of values per point on these spaces, and we can capture that. So altogether, I just think it's fascinating that these relationships are mathematically preserved during the transition from word to context vector, and that's very cool. To me, at least. I don't know. Maybe you think it's boring, but another thing I just want to throw out there to help jog your brains about how this stuff is being used in the real world is think about how you would combine this with other techniques. Now, everything in the real world is way more complex and powerful and crazy and fun and blah, 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 blah. But, we're walking towards the real world here. So how might you take things that we learned from n-gram modeling and combine them with what we've got going on here? So remember, text completion, right? Text completion on your phone's keyboard. The n-gram model under the hood is saying, hey, based on what you've typed before, here's what I think you might type next. But you could extend this to include a new step, right? Instead of just selecting a word at random, you could actually include a step where you evaluate which possible next word best fits the context vector, right? Look at the words that have been typed recently, look at the context vectors for various words in the options list, and maybe even bring in other words that aren't in the most recent options list. Doing so, you can create this interesting tension between what's explicitly likely, based on the directly observed stuff we see in the n-grams, and what's creatively possible based on this sort of broader, more agnostic accumulation of the mathematical meanings of words, right? So you might bring in a word that has never occurred in sequence here, but it still makes sense contextually. It still makes sense in terms of the semantic meaning of the word. So a difference between sort of this tension between what exactly has happened in the past and what is sort of theoretically possible in a different from the context. Anyway, that's the idea of these different techniques of how you might combine them together. I hope I've given you some insight into how these tools sort of come to exist, or not just these tools, but the idea of capturing semantic meaning. in a mathematical form. Now, before we leave, I need to give you another take on all of this, which is the idea that remember that none of this happens in a vacuum. Nothing is idealized. Nothing that you're going to generate from actual human text is going to be, quote, objective. So cultural bias is always going to be in your language. So we're always building our models of language in the context of the real world. Our models will always encode the world as it is in its existing context. So it's never going to be devoid of inconsistencies, falsehoods, absurdities, idiocies. Essentially, because language is recorded by humans, it always comes with the full suite of human cognitive biases. There's a little bit of mildly triggering content to follow. Just hang in there because it's really important to understand this stuff because it's happening in the world no matter what we like or not. So, bias in relational vectors, for example. Here's what we were doing before, right? Remember those relational vectors where we can say, ooh, apply the one relationship between, say, Paris and France to Tokyo and what's X? Japan, right? Okay, Paris is the capital of France. Tokyo is the capital of Japan. Okay, cool. Now we can get into gender roles. So ask father is to doctor as mother is to nurse. Okay. Now, that's not to denigrate nurses. They, in fact, do a lot more of the work than we ever give them credit for. But it's still a little bit unfortunate to see this stuff be gendered like this, right? There's a huge amount of female doctors. There's a huge amount of male nurses, right? Keep going. Man is to computer programmer as woman is to homemaker. Again, not to denigrate the work of a homemaker. In fact, it is one of the most underappreciated, underpaid positions in the world. But these are the kinds of things that, in studies like this, here at the bottom, that Bolubsky et al., this is the way that biases get encoded into systems that are absorbing, semantic vectorized information. We can keep going. Greenwald et al. Did the study, the implicit association test. The general idea of that study was figure out how are concepts associated, flowers and insects, pleasantness and unpleasantness, right? And the whole idea was to study using these measuring, latencies and categorization. How long does it take you to categorize something? Whatever. It's a fairly straightforward study. You can examine it another time, but the psychological findings, at least as far as U.S. participants go, and this is why the study became famous, is that African American names are associated with more unpleasant words than European American names. And this is even if you are African American. You end up with this cultural bias kind of steeped into your way that language works. Yuck. Oops. Male names are more mathematical. Female names are more arts. A lot of you probably know there's a boatload of female computer science students. They're not all artists. So the point is that these biases exist. Old people's names associated with unpleasant words, young people with pleasant words. Point is, all of these are just ways that we humans have absorbed these cultural biases in the way that we use language. The question is, does this translate to, hey, I'm just a researcher, I'm just a computer science researcher, I'm just mining text from the world. My research is fully objective, yes? Well, Kaliskin et al., 2017, would beg to differ. Replication of Greenwald, but instead of using human subjects and experimental, procedures to, have them categorize things, this was just using computed word embeddings. Guess which kinds of names had more similar embeddings to unpleasant words and which names were closer to pleasant words. Unpleasant words like abuse, ugly, stink. Pleasant words like love, peace, and miracle. Leroy and Shaniqua were a little further left than Brad, Greg, and Courtney to the right there. Point being, just because your model is based on data does not make it true, you idiot. Don't be an idiot. And I mean that. because this is something that you can work to avoid, and something that everyone needs to start to work to avoid, because these kinds of things are just getting into systems that help make decisions. That's not super great. Now, there is an upshot to this, and that is that you can just use these kinds of measurements, consider it a detection tool. So you can actually see shifts in culture over time. So, example, we can chart the shift in mathematical relationships between embeddings as they exist over time in the way that language is used. You know, we've talked about how Google has these ongoing book project where, you know, they capture over 100 years of written material. You can run these kinds of things and you can come up with these connections, like, for example, this study, Garg et al., shows a change in the associations of the word Chinese, as in the nationality, with adjectives framed as othering, like barbaric, monstrous, or bizarre. Again, gross, but you see a decline in this US corpus, right? This decline in the similarity rate between Chinese and all of these weird negative othering terms over an 80-year period. This isn't to deny that there is still a lot of work to be done, but the point is that it is nice to be able to look at that and see how these things shift. So the mathematical change is still something that we can keep track of. It's great in that sense. It's also dangerous. So, point being, great power, great responsibility. We've seen how fascinating and potentially powerful it can be to capture meaning from language in the natural world. And the power of mathematically extracting analogies is really cool, right? But we also have to always be aware that these meanings reflect what the system studies. That is the flawed human reasoning of natural language out there in the world. And always remember this word, GIGO, garbage in, garbage out. If your system is eating garbage, it will produce garbage. That's not to say that all text is garbage. In fact, I think it's some of the most fascinating stuff to be able to study things as they exist, right? If you're a scientist, you're trying to capture nature. You're trying to understand things as they are. Just don't start using a corrupted form of that to create robo-judges or whatever. So, continuing the summary of what we've talked about today, we often want to understand whether two words are in some way similar, either in their meaning or their usage or by some other relationship. To compute such things, we're inclined to use math. Vector mathematics help us understand distance really well. So using these bag of words approaches, we can construct context vectors for each word in language. And while this captures a surprising amount of meaning, including relationships between concepts, it also captures plenty of bias, so build or beware. That's it. As always, here's a final thought. Consider other things in the built world that rely on similarity. For example, Amazon's or YouTube's recommender algorithms that suggest similar content or products. Using what we've discussed here, try to explain how these algorithms might work. What may be going into their vectors for comparison? Just language? Or other kinds of information too? All right, that's it. Thanks. Take care.